All right. Well, good morning, everybody. Or I guess it's uh, morning out here. But thank you so much for attending. So my name is Sean Cross. I'm a PhD student, and I study human-computer interaction here at the University of California, San Diego. And I spend a lot of time thinking about data science education. And so, of course, I try to keep my finger on the pulse of how people learn different computational skills. So one day I was browsing one of my favorite sources of, reliable scientific information. And of course, I'm talking about LinkedIn.com. It's supposed to be a joke, but when I came across, I came across this graphic on LinkedIn called Paths to a Career in Data Science. This appears to be some kind of subway map. And you can see different stations, each represent a skill that a data scientist is supposed to know. It looks like maybe each subway line is supposed to be some overarching topic that connects these skills. Now, I don't know about you, but when I saw this graphic, I was pretty confused and overwhelmed. And it got me thinking, because, it's not just the careerists on LinkedIn who are interested in data science. Lots of academic institutions are also very interested in teaching and learning data science. In the upper left, you can even see Bill Nye the Science Guy at the opening of our own data science institute here at UC San Diego. And so thinking about these issues, I was talking to my advisor, and we were curious about what data science educators are actually doing, and specifically what challenges do data science instructors face? How do they cope with these challenges? And also, what teaching issues are specific to data science education compared to statistics education or computing education, both of which fields have now been studied in some depth for a couple decades. So in order to investigate these issues, we conducted 20 semi-structured interviews with people who describe themselves as data science instructors or data science educators. So we tried to recruit participants, with a broad range of backgrounds, and also people who teach in lots of different settings. So some instructors that we interviewed teach thousands of students online. Other instructors, teach small workshops that maybe just have a dozen students in them. And so, I know there's a lot going on this table, but, we tried, as you can see, we tried to get like a 50-50 split between, whether or not our participants work in academia or industry. And, in order to make this table a little bit less confusing, I want to highlight 3 of the instructors that we spoke to. So one of the instructors has a PhD in neuroscience. He currently works for an American professional sports franchise, and he does instructional live streams of doing data analysis on Twitch. If you're not familiar with Twitch, it's a website that, among other things, it allows you to broadcast your computer screen live, kind of like what I'm doing right now. So he writes code and does analysis, in a computing IDE. He broadcasts that live, and then he has a chat room where he has ongoing conversations with people who are watching his stream and watching his live analysis. So another one of our instructors that we interviewed, she has her PhD in psychology, and she's a professor at a medical school and does the pretty traditional teaching, of medical students in a formal in-person setting. And then another one of our participants has a business and mathematics, a bachelor's degree. He started up his own startup, that among other things, it delivers MOOCs. When I say MOOC, I'm talking about, these massively open online courses, which are these online courses that usually cost little to no money, little money that is compared to, enrolling in a course at a traditional university. Where you enroll online, there are lectures online, and you participate in the class through online discussions and assessments and assignments that are administered and graded online. So now that you have some background about who we spoke to, I want to talk about some of the key points that came out of these interviews. So one of the themes that presented itself early on in talking to these instructors was that students come to the data science classroom with a wide range of backgrounds and prior knowledge. So some students have never coded before, so they're at the same time that they're learning the nuances of doing data analysis, and they're learning different statistical strategies that obviously pervade a lot of the material in data science classrooms. They're also learning the syntax of programming languages, and they're struggling with some of the learning to code growing pains that have been well studied in the computer science literature. However, there are also lots of students that are kind of on the complete other side of the spectrum, where they might be professional web developers who come into the data science classroom with years of programming experience, but they're looking to retool and change their careers or get a new set of skills. So what P17 is talking about here in this quote is that many data science instructors that including themselves and instructors that they know were feel that they're self-taught, they're kind of autodidacts, and most of what they learned is from reading books and reading online and playing around with analyses on their own. And they taught themselves a lot of data science skills, but one of the most important skills that they feel they know is this ability to teach themselves, and they feel a need to impart that skill onto their, to impart that skill to their students in order to keep up with a field that is changing as rapidly as data science. And I'm going to come back later and talk a little bit more about that. We also realize that students usually come into a data science classroom, in this case where, they're natural scientists, or, they're studying the natural sciences, and they're already deep into a data collection or an experiment. And what's happened to them is that the amount of data that they're collecting, or the sophistication of the analysis that is required for their experiment, has totally outgrown their skills. So most of the time, they've outgrown, common, environments like Microsoft Excel or other spreadsheet software. So they they believe that, learning some new data scientific techniques may be the key to them having a better understanding or a better ability to do their analyses. We also find that a lot of students come into the data science classroom and they want to learn one thing that maybe they've read about online, that they could just, if they could just learn one piece of data visualization software, like for example, if they could just, learn ggplot2 and, have a better grasp of making statistical graphics, that it would, totally, if they can just get this one technology down, it would totally transform how they do their analyses. When in reality, these students really need to understand, that one tool, ggplot2 is a perfect example in terms of how that one tool fits into a larger data analytic workflow that instructors are trying to teach their students. So what we believe that students are doing here is that, they are satisficing. They have one goal in mind, and they're trying to optimize to learn the strategy that would serve them best. And therefore, they're satisfied that learning strategy will solve their problem in the current moment, although it might not carry on to future experiments and to future data analyses. There are many layers of technology that go into doing data science, and it requires the ability to deliver that technology. And also, there are lots of mental models that go along with this technology, and they are relatively challenging. And so I want to take a moment to talk about these technologies. So, when we think about data science, we're probably thinking about kind of like this high level of sophisticated software, whether you're in, the Python or the R programming world, you're using, pandas or dplyr to do, sophisticated manipulations on data frames. Maybe, you're doing some elaborate data visualizations in order to communicate, to communicate your data set and so forth. But of course, all of these higher level, data science tools rest on top of these base programming languages. So you have to have some fundamental understanding of Python and R in order to kind of, work inside of these programming environments in order to do data analysis. And then, if you want to communicate using those data science tools, and if you have an understanding of these languages, you're going to have to actually do the work in some kind, do and communicate the work in some kind of environment. So maybe, you are putting together some kind of report, and therefore you need a computational narrative. So that might, take place in our Markdown. if you're working in the Python world, it might take place, in a Jupyter notebook that then, you can share. And both of those documents can also kind of be shared data science computing environments. But if you have this software stack of programming languages and then tools that are built on top of them, you're probably going to have some experience managing, packages in R, packages in Python, different versions. And if you're writing scripts, or you're writing other plain text like R Markdown documents, or even Jupyter notebooks, you might want to keep track of versions and the development of these analyses, and therefore you need to understand some Git or some version control. And then, of course, all of this kind of lays on top of the underlying, operating system needs that these technologies are built on top of. So you might have to manage this and install all of it on the command line. You might be accessing programs that are, perhaps specific to the domain that you study. And therefore, you need to incorporate those into your Python or R analysis, and that might also, involve some scripting. And then, of course, if you want to share that analysis and you want other people to be able to build on top of it, it's one thing to share, just like a notebook environment, but ideally you want to share, your full computing stack. So, that reproducible infrastructure might look like Docker containers. It might, be a series of virtual machines that you want to run in parallel. So, my point is in showing all this is that, there are a lot of levels of understanding in this data science stack that interact with each layer interacts with other layers in various ways. And so instructors have to keep this stack of technologies in their head when they're developing courses and when they're teaching. And then, of course, students have to learn about this stack, and they have to figure out these relationships and and how to effectively use the stack of technologies. But what I am really interested in is how instructors think about how their students are thinking about the relationships between these technologies and how to use this data science stack. And of course, this informs how instructors are going to structure their classrooms. So we found that instructors do this. They use really like one of three strategies, is what we found, in order to deliver the data science educational experience to their students. So in the first case, which we call the desktop case, students learn to configure everything on their own computers. Students usually bring a personal laptop to class, and they install that entire technology stack on their own computer, and they manage it themselves. And as you can imagine, there are several cons to this approach. Of course, with all different, with students bringing very different computers to class, they have different issues that come along with installing and maintaining all this software. But there are also, we've heard some pros to this approach, insofar as that students gain an authentic programming environment. In other words, their programming environment looks like the environment that they're going to be using when they're doing real analytical work, whether that's out in the real world at a job or in a laboratory or so forth. And we also heard from instructors that on the job market, in job interviews, that people who are recruiting data scientists out of college expect them to be able to set up their own programming environment, or at least to be able to work with the IT department in their company in order to set up that environment. So the second strategy that instructors use is what we call the server setup. And that's where instructors manage a lot of the behind the scenes technical infrastructure on servers themselves. And then they serve that data science programming environment to students, usually through a web browser. So, students just open up their web browser and they can log into an IDE or a computational notebook, and they can just start writing data analysis code and playing with data. So this approach is nice for students because they don't have to set up anything themselves, and they can just dig right into doing and practicing data analytic coding. However, students need to then maintain, or excuse me, instructors then need to maintain all of this server infrastructure. And they also need to find funding, need to find institutional resources that can support this infrastructure in the long term. The final approach, with these web applications that will just serve a data analytic kind of computing environment. So These web applications are usually run by private third parties, for example, like dataquest.io. And what they do is that an instructor writes their entire lesson, either within this web application itself, or sometimes they can write it in a plain text document. They then upload it to the web application, and then students can go through, and the web application will serve them a programming environment which kind of looks like an IDE, and they can execute code and make visualizations and models. And the idea is that these web applications walk students through a lesson in doing data analysis, and then it also provides quizzes and assessments for students along the way. So one thing that we learned in talking to instructors about these web applications is that they can occasionally be problematic. For example, sometimes these web applications serve up an emulated or a not entirely authentic version of the programming experience that students would have if it was on their own computer. So code that's valid on these web applications might not always be valid in a real computing environment. And then the opposite also happens, where code that is valid in these the code that's valid in in these web applications was then not valid in an authentic environment. So along the lines of these issues, a major pain point that we also found is that it's very difficult for instructors to find and curate domain-specific data sets. So a lot of instructors want example data sets, they want example data sets to teach with that are specific to what they study. Whether they're a geneticist or an astronomer, or they work in fisheries management, they want a data set that looks like the kind of data that they work with in their scientific investigations. So that means that not only do instructors, not want to settle for the classic canonical teaching data sets that come with software packages or are out there on the web. I mean, we all think of MT-CARS and IRIS as the first things that come to mind. But they also, they specifically want data sets that show relationships between variables that are specific to their scientific expertise or to their scientific domain. So, and not only do they want these data sets to be, to address the specific topics that are being taught in class, but a lot of instructors also also indicated that they want these data sets to be messy in a specific way. So, a lot of the time, let's say you're collecting data from a radio telescope or from a governmental office, the data will be poorly formed, and it will, or it'll be, you have to transform it some way for a downstream process. And instructors want the most authentic looking data that not only describes phenomena for their science, but is also messy and poorly formed in ways that are specific to their field. So this is something we can all especially relate to right now, but finally I want to talk about this common theme of coping with uncertainty and stress. Data science is a rapidly changing field. And a lot of instructors talked about how even when they think that an API for a certain software package has become the standard, or that it's stable, a year later the technology will completely change, and the course materials will need to be rewritten. And so sorry, I just wanted to make sure that I'm not running out of time. So instructors are always needing to do some retraining themselves. And as we discussed before, this retraining that instructors feel they need to do, this teaching yourself new skills obviously is part of what instructors want to, is obviously a skill that instructors want to convey to their students. So instructors show their students the right way to further cope with this uncertainty, via a few strategies. One strategy that a lot of people talked about was live coding in front of their classrooms, so that, inevitably they would make some mistakes while they're live coding. And, when they make these mistakes, they can show students how they recover, either through debugging strategies that they want to demonstrate to their students, or even, they go online and find help like the rest of us, and they want to show that process to their students, and to also normalize that process for them, so their students know that that's okay. So now, of course, I'm thinking about how we can make this whole learning and teaching experience better. So if you want to find data sets right now as an instructor, of course, there are data repositories like the NCBI or like data.gov, but they, there aren't necessarily repositories where you can search and look for certain statistical features or even certain relationships between variables. And so, two solutions, or at least two approaches that are on the top of my mind in terms of making, in terms of improving this classroom experience is, giving instructors or giving anyone the ability to sketch high quality data sets for teaching, and thinking about new data science learning environments to better help instructors and students scaffold their knowledge into this data science technology stack. So I'm going to show you a very short and crude demo of what I mean by sketching high quality data sets for teaching. Something that we're working on, with my colleagues and my advisor right now, is basically how you could visualize a data set in several dimensions, and then try to directly manipulate or draw your own relationships between the variables in order to have better and more intuitive tools for crafting a data set. So I want to thank you all for attending this talk. I really enjoyed it. I wish I could be with you in person, and I'd be happy to talk and to answer any questions.
Great, thanks very much, Sean. And remember, everybody, to just pop your questions into the Q&A if you have questions for any of our speakers. This is a really fascinating talk. A question I had about sort of sketching out data sets. Do you envision that to be something where people will generate their own, or will it where that sort of sketching feature will help to sort of identify existing data sets that have features that look like the ones they're sort of after?
Sure. I mean, what I'm like the work that we're doing right now is, so it's funny, the work we're doing right now is, in terms of developing the tooling, we're thinking about it as people sketching their own. But I think that, something that, I've thought about from the start is like people bringing in a couple variables into that environment and then wanting to, that from an existing data set, and then wanting to like model other variables based on some existing data. So, I think that, I think that we have to get like the tooling right first, but then, I'm interested in working with folks to see, what their real, what their needs are or desires are in terms of building on top of existing data sets.
Yeah, that makes sense. And then another question I had was, do you think that instructors are, since instructors also have to be adapting to a new environment and learning things on the fly, do you have any thoughts on how we could create instructor kind of train the trainer friendly resources?
Sure. I mean, there, there are a lot of like fantastic kind of like train the trainer resources, that are offered by our studio, that are offered by like software and data carpentry. Maybe you're, the thing is that those programs, I imagine are more specific to like, the Tidyverse and RStudio type of tools, or, in the data carpentry and software carpentry sense, like probably, like more specific to like, just like scientific computing, like general scientific computing skills. And so, the question is like, so the question of like creating things that are more for like specific domain teaching,
Right.
I would love to look at those programs and look at like those train the trainer lessons learned,
Right.
In order to expand it into more like domain specific settings.
Got it. All right. Well, thank you very much, Sean. Again, thank you. Everyone is clapping all over the United States for your talk. And I will, it was a great talk. And now I'm going to turn it over to Nick Strayer, who is going to give us a talk about building a software package in tandem with machine learning methods, to wrap us up. So I'll hand it over to Nick. And if I've missed your question, because we're sort of running a little short on time, I will try to do questions at the end if we have a minute or two. And if not, then you can always tweet the speakers, and then sure they will be happy to answer your questions back on Twitter. All right, so Nick, you want to take it away?
Yes, I think Sean needs to stop sharing his screen real quick. There we go.